All right, the final section in chapter 12, we're going to talk about weight and momentum. So, really cool thing here is that you apply a force everywhere you go. And you're like, what? You have a force wherever you go. And why is that? Because we're on Earth and the force of gravity is acting down on you. So if you ever want to figure out the force that you have, we can take your weight is equal to mass times acceleration. So if we want to revise this, the force of weight or the weight of any object, so we can go F of W, the force of weight, is equal to the mass times gravity. Now, your weight. All right, what is your weight in newtons? Well, that's really easy to figure out. You're going to take your mass, which is going to be in kilograms, and multiply it by g. And remember, gravity is 9.8 meters per second squared. So you take your weight in kilograms and multiply by 9.8. And what that tells you is your weight in newtons. So for example, I weigh 100 kilograms. I'm going to take 100 times 9.8. And instead of saying, right, if you're conscious about your weight, instead of saying, I weigh 125 pounds, all right, if I am Mr. Ryan Recius, I weigh 100 pounds. Oh, 100 pounds, that sounds wimpy. Now, convert your weight to kilograms, which would be like 45 kilograms. You take 45 times 9.8. And if I'm Ryan Recius, I can say I weigh 480 newtons. How sweet is that? Huh? No, I'm not 100 pounds anymore. I am 480 newtons. All right? So something to think about when you're talking about weight and mass. You can take your force is equal to mass times gravity. So your weight can be in newtons or kilograms or, in pounds since we're in the metrics, or not in the metric system in the United States. Next up, if we talk about, last thing I want to talk about for chapter 12 is momentum. All right. We're going to couple mass, but instead of coupling mass with acceleration like we did to figure out force, we're going to take mass times velocity and calculate your momentum. Now, momentum, if we do the abbreviations here, momentum is abbreviated with a lowercase p. You're like, why a lowercase p? Well, lowercase m's already taken by mass. So we have momentum is equal to mass times velocity. Or if we're going to do a circle for that, momentum, little p, remember that's momentum, is equal to mass times velocity. So if you want to figure out the momentum of an object, you're going to take mass times velocity. So just kind of figure that out, and that's what we have. So momentum is equal to mass times velocity. You can really affect your momentum in two ways. You can have a high mass, or you can have a high velocity. So if you think about the game of football, essentially a running back and a defensive lineman who's 300 pounds might have the same momentum. Why? Well, Adrian Peterson, who's about 240 pounds, can run really fast. All right? If you think about it that way, Adrian Peterson can run really fast. His mass is lower than a defensive lineman, so he can run really fast. Likewise, that defensive lineman who might be 320 pounds can run, but he's going to run a little slower than Adrian Peterson. But because he has more mass, it's possible that they have the same momentum. So momentum is equal to mass times velocity. Last thing when we talk about momentum is the conservation of momentum. All right, what's the conservation of momentum say? It says that momentum cannot be created nor destroyed, only changed essentially. That means momentum does not increase nor decrease. All right? So momentum, any object that loses momentum, it has to be gained by something else. So if one object loses momentum, it has to be gained by another object. Think of it like this. All right, you're playing croquet or pool. All right? And you're shooting at one ball, and you're going to hit another ball on the table. Typically what happens, you hit the first ball rolls, hits the second ball. What happens? The first ball usually stops and the second ball continues to move. That's a conservation of momentum. Ball 1 lost all of its momentum because it stopped moving, but it transferred it to ball 2, and ball 2 kept moving. So we're going to do a little bit with momentum and kind of talk about how momentum works a little bit and how momentum can be conserved. But if one object loses momentum, another object has to gain all of that momentum. Momentum in the universe is always conserved, which means we never lose momentum ever. So just kind of an idea with the law of conservation of mass. So this concludes momentum. This concludes section 12.4, and it concludes 12.4, and it concludes chapter 12. This is Mr. Kletter, and I'm signing off.